Hello. Okay, we just have a couple of quick more bits of information that I want to give you before I have you go forward with the test. And so let's get into that. So really what we're going to talk about today is high-flying birds, the respiratory challenges that high-flying birds have to face, and then also the ways that they solve those challenges, and then also do a quick survey through the animal kingdom of respiratory pigments, and really just talk about all the different kinds and colors of blood that there are out there. So, hey, let's go ahead and get with it. So let's talk about just how high do birds fly. And these two highest flying birds, I'm looking for my pen here because, I like to draw things. Okay, so the two highest flying birds here are the bar-headed goose, and we know that gets up somewhere around 9,000 meters because people have stood at the top of Mount Everest and seen them flying over the top of Mount Everest. And Mount Everest is just below 9,000 meters, the peak of it, and bar-headed geese have flown over the top of that, so we know that they get a little bit higher than that. And then also, so that's the second highest. The highest that we've ever seen, is this Ruppel's griffin, or also known as Ruppel's vulture. Now, the highest that we've seen that go is 11,278 meters, which you might be thinking, wow, that's very specific. Did they, put a tracker on it or something? No, actually, they did not. We figured this out in 1973 when a plane hit a Ruppel's griffin at 11,278 meters high. It actually caused one of their engines to fail. They landed safely, and from the remains that they pulled out of the engine, they were able to identify that as a Ruppel's griffin, and that is the highest record that we have of any bird ever. So here we go. This here is a bar-headed goose. This up here, you can kind of tell from the bars on its head. You wouldn't look at this guy and say, "Hey, boy, that's one of the highest flying birds we know of," but sure enough, there it is. And then the Ruppel's vulture right here. I think they look cute. Isn't that a nice looking bird? So anyhow, with that, let's talk. What kind of stresses are these animals going to be facing when they're at these really high altitudes, when they're flying up that far? When they're flying up that far, up that high. There we go. So you have some added stress of high altitude, and one of those is that you're just going to have less oxygen. There's just simply less oxygen to be breathed when you're that high. Now, birds deal with this already in one way that we've already talked about earlier in class, and that's that birds have more efficient lungs than other vertebrates do. But there's a little bit more subtle problem that you have with high altitude flying as well, is that you simply have lower air pressure as well. Now, this causes a number of different problems. One of them, it's just harder to stay afloat. Like birds and planes and all this other things that fly, they fly because they're using the resistance of the air. They're actually pushing off of air, and if there's less air, and it's less dense, it means there's less to push off of, which means that you have to work harder to stay afloat. So they actually need to flap harder than they do otherwise, just because the air is thinner, and this is going to increase their metabolic demand. So it's going to increase their need for oxygen. So again, this is a really good reason to have more efficient lungs. This lower air pressure not only provides you with less oxygen, it also means that you need more oxygen. So you have these kind of double whammy going on. You have less of it, but you need more of it, which again leads to them having much more efficient lungs than do other vertebrates do, because simply you don't ever have this kind of stress on you. Okay. Another thing that is a problem for high altitude flyers that you might not necessarily think of, but it's low CO2, or this thing here, hypocapnia. Hypocapnia is low CO2. Particularly, we talk about this as being low CO2 in tissues, but also it could be low CO2 in other situations as well. But really, hypocapnia, we're talking about low CO2. The opposite of this would be hypercapnia, which is then high CO2. So why in the world would you have this, and why in the world would this even be a problem in the first place? So you get hypocapnia at high altitudes because of two different reasons. Number one is that these birds are breathing more heavily. They're breathing harder, which means they're dumping off CO2 that they're generating in their blood and in their muscles at a much quicker rate than you normally would. One example of this, one kind of parallel to this, is what's known as shallow water blackout if you're trying to swim underwater or stay underwater. Oftentimes what people will do is they'll hyperventilate, or sometimes what people do, I guess not always, anyways. When I was a kid, this is a really common thing, is that if you want to go to a pool and have a underwater competition to see who could stay underwater longer, you would hyperventilate before you go underwater, and it would make it so that you could stay under longer. Now, it kind of sounds like the thing that would be kind of a, I don't know, like just a myth that grows up around little kids, but it's actually true. It actually does help you stay underwater longer. The problem is it's actually really, really dangerous. What happens is that by breathing really heavily, it will drive down your CO2 level. It actually drives down your CO2 level in your blood farther than it raises your oxygen level. The reason for this is that the gradient, even though there's virtually no CO2 in the atmosphere. It's very low. Not virtually none, but it's very low. And the amount that is in your blood is like many orders of magnitude higher. So if I remember right, it's something like you have 500 microatmospheres or 400 microatmospheres of CO2 in the atmosphere, and you have like 15,000 or 50,000, I think it's like 50,000 microatmospheres in your blood. So it's like phenomenally higher, which means that with this really big gradient of CO2 between your blood and the atmosphere, you can actually drive your CO2 really low if you start hyperventilating. But the problem is, on the other side, oxygen, you're not actually picking up all that much more oxygen. So you have about 21,000 or 200, 100. You have about 21% oxygen in the atmosphere. And it turns out your blood, even when it's deoxygenated, isn't driving it that much lower than that. We're talking like maybe down to 16%, which means if you hyperventilate, you can raise it up to about 21, but you can't drive it up any higher than that. You actually oxygenate your blood pretty well, which means that you're driving your CO2 proportionally lower than you're raising your oxygen. And since it is carbon dioxide that is your primary driver to breathe, this actually means that you can hold your breath for longer, because I've actually driven my CO2 in my blood fairly low, and it will delay oxygen getting as high as it needs for you to feel the urge, the drive to breathe. Okay, now this is a problem because you actually have not raised, you haven't elevated your oxygen nearly as much as you have depressed your CO2, which means that it's very possible for you to never feel the urge to breathe by the time your brain runs out of enough oxygen to stay conscious, and you pass out underwater while never feeling the urge to breathe. Okay, so that's a problem. This is a thing known as shallow water blackout. So, I mean, the takeaway from there, don't hyperventilate before you try to hold your breath underwater, because you might just pass out. And yeah. Okay. Bringing this back to birds now. So with birds, this is a problem because they are also in an area where CO2 is very, very low, which means you have this high gradient, and you are respiring more hard, more heavily, because you're flying, and just because of the same reasons that we just talked about, your metabolic demand is higher because it's harder to stay afloat. You're breathing harder than you would under normal circumstances, which drives your CO2 very low. So this is a problem, or would be a problem for you, because this would then decrease your urge to breathe, because the CO2 is being driven so low. This is the reason why hypocapnia would be a problem for any other organism other than a high-flying, any other animal, I guess I should say, other than a high-flying bird when this happens. Because it would make you not breathe. And that's a problem when you really need a lot of oxygen. You really need to breathe. So they have a couple ways around this. First off, they actually are not that sensitive to CO2 to drive breath. They actually use oxygen more than CO2 to drive the urge to breathe. So this hypocapnia, does not decrease ventilation in these high-flying birds the same way it would in you and cause them to not breathe and then, fall out of the sky. That'd be bad. Also, typically, low CO2 would also cause vasoconstriction. Remember, we've talked about the opposite, where high CO2 causes vasodilation. And this is normally good because if you have a certain muscle that's working really hard, it's going to be dumping CO2 into the tissues and into your blood vessels. And that high CO2 is an indication that we need to get more blood to that area. So it causes vasodilation, which will cause more blood to go to that area preferentially. And this is great. Like, this is one of these really cool local controls that we have for moving blood around to the proper spots in your body that you don't really, you don't need some central control. It's a local control that helps control this. So, now this would be really bad in, again, a high-flying bird because you drive CO2 really low. That causes vasoconstriction in a lot of places that you don't want to have vasoconstriction happening because these muscles are working hard. So actually especially in their brain and in their muscles, the vasoconstriction dilation of these these blood vessels, not capillaries, it'd be arterioles in this case, is not sensitive to CO2. So low CO2 does not cause vasoconstriction. So hey, that's kind of cool. You normally wouldn't think of low CO2 being a problem for birds flying really high, but it is. Okay, so we have that. We also have another issue here, is that high-flying birds just tend to have larger lungs than other birds do. And this increases the amount of gas exchange surface that they have, more of the air capillaries that they have. So, hey, that's also a big thing. So they both have these very, very efficient lungs, like most birds do, but then they're bigger than most other, the language of English, most other birds are as well. So you have that. So, hey, that's cool. In addition to all of that, they actually have modified hemoglobins as well. What you're seeing here is an hemoglobin oxygen binding curve, like we've talked about in the online lectures before. And what you have here is you have a duck there and a Canada goose there. These are other Anseriformes, so these are closely related birds in the same family as they are. In fact, one's a goose, like it is. And again, remember, we have this sigmoidal curve. You're looking at oxygen pressure, partial pressure in the environment on the x-axis, and then the amount of oxygen saturation hemoglobin on the x-axis. So how much of the hemoglobin that can be bound to oxygen is bound to oxygen. And what you see here is the bar-headed goose has this left-shifted oxygen saturation curve, meaning that's going to grab onto the oxygen much more tightly than it does these other birds do. But here's the thing. Here's the cool thing about left shifting of this is that you look over here, like at the upper ends of where you get oxygen. So up here, you actually have a pretty big difference here. And, especially here, like right around in here, it's very big. Like if I look at about 50 torr here, it's a pretty big difference. But if we then slide down to where it's much less oxygenated, like it would be in the muscles, right here, it's much less. What this means is because it's left shifted, but it's not just like this left shift that just takes the entire thing and moves it left, it essentially tilts it up instead. It means up at these kind of moderate ranges where you're going to be loading oxygen in the lungs onto hemoglobin. It's very oxygen greedy compared to the Canada goose and the duck here, and it's going to bind to it much better. But the opposite could be the problem if you get down into the tissues and it doesn't release the oxygen back into the tissues to oxygenate the tissues. If it's still holding on tight to it, that doesn't really help you at all. But down at those lower oxygen levels, it's actually about the same. It's not that much more, it doesn't have that much higher of an oxygen affinity than these other birds do, which means that's releasing it about as easily in the tissues, but it's just grabbing onto it much more tightly in the lungs. So again, it's a left shifted, but left shifted in a way that's not like a uniform left shift. It's like a left, I guess it'd be like this way, left Wait, no, this way. Left, tilt, like that. There we go. It's backwards to me. Okay. So, a couple other things that they have is they have this really high capillary to muscle area. It's very high capillary density to muscle area. This is due to a couple different things. Number one, they just have more capillaries. The capillary density in their muscles is just higher. And so, again, what this does is it shortens the diffusion distance between the blood carrying the oxygen and the muscles that need it, which means that if you're shortening that diffusion distance, the oxygen is going to be dumped off and get to where it needs to go much more quickly. And so it's more efficient at delivering oxygen. In addition to this, you also have smaller muscle fibers, like the individual muscle fibers especially the flying muscles of these high-flying birds is also smaller. And you have this rearrangement of mitochondria as well that lines them up more closely to the blood vessels as well. So they gather, all these mitochondria gathering in cell areas nearest the capillaries. So again, another way that you're shortening that diffusion distance between the mitochondria that are the specific place that we need the oxygen and the capillary, the specific place that's carrying the oxygen. So as much as we can shorten that diffusion distance there is going to make it more efficient and quicker delivering the oxygen. Okay, so that's really what I got on some adaptations, some respiratory and cardiovascular adaptations of flying birds. Okay, so with that, let's go ahead and just get now into a quick survey of different respiratory pigments that are across the animal kingdom. This is just cool because this is like different colors of blood. I remember when I was a kid, I remember watching Star Trek at one point, and my dad was also really into Star Trek, and Spock bled at one point. He's bleeding green. I was like, Dad, what's up with that? It's like, well, Vulcans have copper-based blood. I was like, wow, how did they think of that? Well, the cool thing is they didn't actually think of it themselves. It's like a thing that already occurred in the animal world. So, hey, let's go through. And I have color. I've based them on color. Here we go. We have hemoglobin. I'm not going to talk about hemoglobin this time because I've already talked about hemoglobin quite a bit in the online lectures. We're going to talk about these other ones. Hemocyanin, Chlorocruorin. It's like Chlorocruorin. Erythrocruorin, Hemerythrin, and Vanabins. These are just cool. You got like blue, green, red, purple, yellow, all the cool colors. Don't do that on me, please. Here we go. Okay. So first up, this that you see up here, that is the blood of horseshoe crabs that we actually collect because we use it as a way to do quality control on some drugs and stuff like that. Apparently it coagulates with impurities pretty easily, and so we can use it as this method for testing for impurities. Anyhow, that's not the reason I'm showing it to you. This is the reason why they're all lined up like this and being bled. But their blood is a good demonstration that their blood is this bright blue color. It's not the red that you typically think of. It's this bright blue. And it's because their blood, the respiratory pigment in it, is this thing called hemocyanin. And hemocyanin is this oxygen respiratory pigment, or this oxygen-carrying respiratory pigment, that instead of having iron as the metal that you're coordinating the oxygen to, it has copper. And you have 2 coppers per subunit, but you can have anywhere from 6 subunits at the smallest all the way up to literally hundreds to thousands of subunits in some of these animals. Especially octopuses and other cephalopods have, like, I think octopuses have a barrel-shaped hemocyanin that has like 300 to 500 subunits in it. They're crazy compared to hemoglobin that just has like the 4 arranged in the diamond. Hemocyanin is like a whole nother thing. And hemocyanin, you find it in arthropods, like what you were just seeing with the horseshoe crabs in the previous slide, but you also find it in mollusks. Things like snails and clams and, of course, octopuses. Octopuses have blue blood, by the way. That's another thing that makes them super cool. Yeah. So, and another big thing, and this is one of the big reasons why you have it in many subunits, especially in some organisms, is that unlike hemoglobin, that often in vertebrates is being put into like a blood cell, like you have your hemoglobin in red blood cells. It's not in a blood cell. It is free floating in the blood. Now this becomes a big issue sometimes because with red blood cells, the red blood cell is not going to leak out of your blood vessels because it's too big. The problem is that, especially with some of these organisms that do have a closed circulatory system, like cephalopods, they have a closed circulatory system, but they use hemocyanin. But one of the problems then is if you just had like 4 subunits of hemocyanin, it would leak out of the blood into the tissues, and you don't want that. You want the hemocyanin to stay in the blood. And so what you do is, instead of having these blood cells that you stick it into, you just make the hemocyanin huge. And so you can make it have like hundreds of subunits, and therefore it's so big that it will not leak out of the capillaries where you have all the other things that you want to leak, like water or like plasma or lymph or whatever it is. You know what I'm talking about. You don't have fluids leaking out and small osmolytes and other stuff like that you want to have leaking out there. But you don't want your hemocyanin. You don't want your hemoglobin either, but you put it in a blood cell. Cephalopods and other things that use hemocyanin can't do that, so they tend to make hemocyanin really, really big. Another thing that you can get by having it really big is more cooperativity. So remember, again, like what we see in hemoglobin, that after one of the subunits binds an oxygen, it actually makes the other subunits more likely to bind an oxygen. It raises their affinity. You see the same thing in hemocyanin. So hemocyanin has cooperativity as well. More subunits gives you increased cooperativity, actually, in some cases. Now, in addition to this, you also have this really large Bohr effect. So again, if you remember, Bohr effect is the influence of CO2 and pH on the affinity, where if you have higher CO2, lower pH, it decreases the affinity of your respiratory pigment. In other words, helping it drop off the CO2. And if you have low CO2 or high pH, it tends to increase the affinity or let it grab it. Now, this is normally a really good thing because it means in active tissues where you have high CO2, low pH, it's going to drop off oxygen in those places, which is what you want. Now, in animals that have hemoglobin like the Bohr effect is just one of many different things that help modulate the affinity of hemoglobin for oxygen. But it turns out hemocyanin actually doesn't have that many things that will modulate its oxygen affinity. So its Bohr effect tends to be exaggerated because you're trying to get the same level of modification of the affinity with fewer things. So those fewer things actually have to do more, like the Bohr effect. Also, it has just overall lower oxygen affinity than hemoglobin does at high oxygens, at like normal oxygen levels that you're used to. It actually it's not nearly as efficient as oxygen, not as efficient as hemoglobin at carrying oxygen. However, especially at low oxygens and low temperatures, it does quite a bit better. So that's kind of an aside there that's interesting, is that often you will hear, oh yeah, hemocyanin is not nearly as good at hemoglobin carrying oxygen. That's true. If I were to stick you with a bunch of hemocyanin, like if I were all of a sudden replace all your hemoglobin with hemocyanin, it would suck. It wouldn't work well at all. But that's because you live in an environment that is high oxygen and your internal body temperature is relatively high. However, if I put you in an area of low oxygen that's relatively cold, your hemoglobin would not do nearly as well as hemocyanin does. So, something to keep in mind there. Okay, so let's talk about hemocyanin is kind of a weird thing because we talk about it as if it's one thing, but in truth, it looks like this is a case of convergent evolution, that two completely different clades have arrived on essentially the same thing. So, if you look at, this is like family tree of animal life here. Here are the arthropods down here. And then the mollusks, get off there. Mollusks are up here. They both use hemocyanin. Look how far away from each other they are. This is not like the same thing. It actually turns out if you look at molluscan and arthropod hemocyans, They are different. They're not like exactly the same hemocyans. So here, if we look at it, looks like there's some tyrosinases, some copper proteins that looks like they're derived from, and it looks like it looks like the molluscan hemocyans come from a pretty distinct branch from arthropod hemocyans. Now, it looks like they're actually kind of derived from a similar copper protein if you go back far enough, but if you look at the most similar other copper-containing proteins in both of those, they're not related to the exact same things here. And it looks like, and molluscan hemocyans and arthropod hemocyans, they are much more closely related to each other than they are to the other group. So, like, we call them the same things, and it looks like they both kind of hit on deriving their oxygen respiratory pigment from the same basic type of enzymes, but they're not the same. Okay, so that moves us on to the next one. Let's talk now about green blood, and this is chlorocruorin. Or, man, this is always a hard one for me to pronounce. You just think of this, rorin. This is rorin. Chlorocruorin. Rorin. Okay. Chlorocruorin. Okay, so this actually is going back to an iron-based one. So this is an iron-based oxygen-binding protein oxygen respiratory pigment. And in this case, instead of like hemoglobin having a bunch, it actually is just, instead of hemoglobin having 4, this has a bunch. And so the actual individual oxygen binding subunit looks a lot similar to myoglobin, but then between all these individual subunits, you actually have this completely other protein that's not oxygen binding that links the individual subunits of chlorocruorin together. So that's how this ends up being put together. Okay, so this is found in some annelids, some like ringed worms, not ringworms, but like segmented worms. And actually, I don't know if ringworms are. No, ringworms is a fungus. Like ringworm is a Okay, back on focus. I'm back with you. Okay, anyhow, so these are the segmented worms. Some of them have chlorocruorin. When it's oxygenated, it is green. When it's deoxygenated, I do not remember what color it is. Maybe I don't know. And again, like what we saw in hemocyan, it's free. It's not bound in the blood. So it's just out there hanging out as well. And again, another reason that we have hundreds of subunits, not just 4. Again, annelids have a closed circulatory system like the cephalopods do. So they do not want this leaking out into just out into their tissues. They want to keep it in their circulatory system. And so you need to have it big in order to do that. Chlorocruorin has relatively high cooperativity. It also, like hemocyan, has a pretty large Bohr effect. And overall, it has pretty low oxygen affinity as well. So, again, another thing that just, this one, there's not any... I don't know that if you get low temperatures, low oxygen like you do with hemocyan, that's particularly good as well. But then again, it's in animals that aren't that super metabolically active, so it doesn't really need to be as good as hemoglobin or other things like that. Okay, let's go on to the next one. This is an earthworm that's all opened up, and in this case, what we have is this kind of red blood here that looks very much similar to yours. You also remember this is another annelid. It has a closed circulatory system, so if you look really close, you can see like little vessels in it, like right here and through here. Again, this is an animal with a closed circulatory system like what you do, and their blood actually looks very similar to yours because, again, it's using a respiratory pigment that's actually fairly similar overall to hemoglobin, but it's not hemoglobin. In this case, this is erythrocruorin. And erythrocruorin, actually, the individual subunits are functionally identical to hemoglobin. It essentially uses the same subunit that hemoglobin does. But instead of actually just having a normal, like, hemoglobin with the four subunits in, like, this diamond shaped, instead, it has 144 subunits. Like, 12 sets of 12, I think. Anyhow, And what happens is that it uses, again, like we saw with chlorocruorin, it uses a linker protein between them to actually stitch them all together. So what you have is you have this 12 sets. Okay, which one? Right here, this is 12 subunits of hemoglobin right here. And then you have a linker that then links it to another 12 sets of hemoglobin right over here. And then you get a barrel of these that's 6 on top, 6 on the bottom, so for another 12. So essentially what we're doing is we have 12 sets of 12 here. We have a lump of 12 hemoglobin units that is then bound to this linker protein. Those are all linked to this linker protein, and this linker protein will also then bind it to another kind of complex here as well. And then that forms this barrel-shaped that has kind of 2 layers here. We have 6 of of these 12 complex, like these 12 hemoglobin complex units in one set here. Wait, that's 1, 2, 3, 4, 5, 6. Not these ones. 6. And then 6 down below, kind of shaped in this. It's like a big donut. It's like a big blood donut. Okay, never mind. I'm not going down that way. Anyhow, in the end, it's red. It's basically hemoglobin, which means that it comes out like, again, looking very much like your blood, hemoglobin-like. Yeah. Now, this again is found in some annelids, including earthworms. So when you open up an earthworm, it has erythrocruorin in it, and it is red blood because it has this. And again, it's free, it's not bound in blood cells. Again, you have an animal with a closed circulatory system, but no blood cells like that carry the respiratory pigment. So we need them huge so that they stay inside the word circulatory system. Thank you. Like with the other ones we've seen, it has high cooperativity, it has a large Bohr effect, and it has relatively low oxygen affinity. Now you might think, why in the world is that? Honestly, I don't know. I don't know why erythrocruorin has such worse oxygen affinity than hemoglobin does when it's basically using hemoglobin. I'm not sure on that one. Okay. So, there we go. So, next one up is Hemerythrin. Now, Hemerythrin is kind of interesting because it uses iron. Like, you've noticed we've only used 2 different metals up until this point. We've used copper in Hemocyanin, and then, like, everything else is using iron. Iron is really good at binding these. And all of them have actually used iron in a porphyrin ring. Every single one of them up to this point. Now, Hemerythrin decides to do it different because it doesn't use a heme-like structure to do this. Why do they call it Hemerythrin? Well, the heme refers to blood in this case. Yeah. So, anyways, what it's doing here... Hold on here. Let me just pull this up like this. Yeah. So, okay. So it's bound to the carboxyl groups on glutamate. So here we have these carboxyl groups on a glutamate. And then you have I think one's a glutamate, one's a aspartate. And then what we have is we have these histidine residues also over here. And all of these then are kind of binding. So the histidine's over here and over here. And all these are kind of binding to and holding this iron. And that's the iron then that is going to bind the oxygen. Yeah. Where is it? Like here. There you go. So it's binding that oxygen there. It's weird. It's different. Like they're doing it a different way. And again, this is like when this is oxygenated, it looks purple. When it's deoxygenated, I do not remember what looks like deoxygenated, but it's purple blood. Hey, so that's pretty slick. And this is found in a lot of kind of like odd and end kind of organisms. So we find this in sipunculids, which are these right here. They're a type of worm. It's found in the priapulids, which is another kind of worm. Marine worms. Both of these are in marine areas. It's found in brachiopods. This is a brachiopod right here. Now the brachiopods are cool because they look like clams, but they ain't clams. And they're organized nothing like clams on the inside. And it turns out like they were all over in the oceans before the clams were in the oceans. It's really kind of cool. And it also happens to be like one annelid genus. And I have no idea why it's in one annelid genus. This just blows my mind. It's in this one, Magalona. There you go. I I don't know why that one. Okay, so that's Hemerythrin. Again, this is free and not bound in blood cells. This is something that's going to come up over and over again. And most Hemerythrins do not show cooperativity. So unlike what we've seen with basically every other oxygen transport protein up until this point, it's not cooperative. We actually don't know much about Bohr effect on this, so there's not really good evidence whether or not there is or is not a Bohr effect, and it also has very low oxygen affinity. In this case, it's quite a bit lower. It's only about a quarter that of hemoglobin, so it's significantly lower. Okay, so let's get on to the last one, the yellow one, and those are the Vanabins. It actually turns out that we're not exactly sure if they're used for oxygen transport or not. And I mean not sure as in it binds oxygen and it carries it around the body of the organisms that have it. We're just not really sure if it's meant to do that or not. I'll come back to that and let's talk about it. So first off, let's talk about the metal that's in it, and it's vanadium. So this is kind of out of left field. So this is just all the way out. Up until now, again, iron has been a big popular favorite of animals to use as their oxygen binding protein, and then copper is used by a lot of, not by a lot of groups, just mollusks and arthropods, but again, mollusks and arthropods are two of the most abundant organisms on Earth, animals on Earth, let me say animals, not organisms. So yeah, hemocyans get used tons, even though it's not numerically a ton of different groups. But vanadium's out of nowhere. So this is really weird. And these are found in tunicates. So these are a deuterostome, and they're kind of interesting. They're little organisms that then attach, they're sessile, and they essentially pump water through them for their entire life. Actually, again, picture of a tunicate. Anyways, they're sea squirts. Another name for them is the sea squirts. So sea squirts have Vanabins. And this is free in the blood. It's just floating around in the blood. Now, here's the deal with Vanabins. Here's why we don't exactly know. They do bind oxygen. And it does kind of transport oxygen around the body, but it doesn't have a lot of the normal characteristics of an oxygen transport protein. It doesn't really show cooperativity, or it doesn't really have a Bohr effect, and there's a lot of things that it just doesn't do. And so it also turns out that Vanabins are really toxic to other organisms. So we're not exactly sure if they are a toxic defense that just happens to also pick up oxygen sometimes and transport it around on accident, or if they're an oxygen transport protein that just also happens to be toxic. We're not sure. So this is kind of an odd one, but still, they're yellow when they're oxygenated, and that makes me kind of happy. Okay, with that, that's all I got on this. That's the end of stuff for the test. So I will see you after the test.